The 56 microsecond failure. An uncorrected atomic clock on the lunar surface will drift 56 microseconds ahead of a terrestrial clock every 24 hours. This is not a rounding error or a hardware glitch. It is a fundamental requirement of general relativity in a lower gravity well. If we ignore this delta, any lunar positioning system will miss its target by over 16 kilometers in a single day. Precision navigation depends entirely on timing, and on the moon, time is literally moving faster. Gravity is a metronome. Clocks tick faster on the moon because its mass is significantly lower than Earth's, resulting in less gravitational time dilation. General relativity dictates that the deeper you are in a gravity well, the slower your time passes relative to an outside observer. On Earth, we are deeper in the well. By the time an Artemis astronaut finishes a standard shift, their onboard clock is already out of sync with mission control by a margin that would break any precision landing software. This is not a theoretical debate. It is an engineering constraint for the 2026 lunar campaign. The navigation breakdown. Modern navigation relies on the constant speed of light. GPS satellites work by comparing timestamps between multiple sources to triangulate a position. If the moon's local time standard is not mathematically tied to Earth's through a relativistic transformation, the distance calculation fails. A discrepancy of just 1 microsecond translates to a 300-meter positioning error. Without a coordinated lunar time, landing a supply craft near the Shackleton crater becomes a statistical impossibility rather than a controlled descent. The problem with relativity syncing. We cannot simply sync lunar clocks to Earth via a radio link because signal latency and the moon's own orbital velocity introduce secondary relativistic shifts. To maintain a functional ecosystem for the 2026 Lunar Gateway, we need an independent timescale that treats the moon as its own inertial frame. Engineering this requires more than just a software patch. It requires a dedicated ensemble of atomic clocks physically located on the lunar surface to define the standard. We are building a local reality, not a remote-controlled clock. The real implication. The move to establish Coordinated Lunar Time proves that the moon is transitioning from a scientific destination into a distinct operational domain that cannot rely on terrestrial infrastructure. The daily 56 microsecond gain, coupled with the critical navigation breakdown risks, forces us to build a multinodal solar system architecture. For mission planners and hardware builders, this means every piece of equipment must now handle its own relativistic transformations locally rather than waiting for a correction from Earth. As we deploy the first compliant hardware late this year, the focus shifts from whether we can land to how we manage a distributed infrastructure that doesn't share a universal present. The real indicator of success will be the first successful autonomous docking using local lunar signals. Watch for the 2026 flight software updates on the Lunar Gateway as the primary validation of this relativistic logic. Subscribe for more